In this tutorial we're talking about tangential velocity and tangential acceleration. To help illustrate the differences between these two types of velocity acceleration and our angular velocity acceleration we just learned, I would like to go to a visual here. Let's say that we have a person running track. So here's the track, they're running in a straight line. Here is the person running. And we're going to plot out where this person is located every second. And let's say that they're running at a constant velocity, so if I plot this out, here's where they start, and 1 second later they're at this spot, and 2 seconds they're at this spot, and 3 seconds they're at this spot. And so we can see that their distances are equal for every second, because it is at a constant velocity. And if I were to draw my velocity vectors, I would say, here's my velocity vector, which is constant every position. Now, what we're doing here, though, is we're talking about rotation, so we're talking about things moving in a circle. So what I'm going to do is take this track here, and I'm going to bend the track. And we still have our person running. Usually this is what happens. The person is running on a curved track. And we'll plot out those points again. Now again, we just curved that track so the points get curved as well. And there's our 3, 4 points. And now we're not going to call these X's anymore because they are arc lengths. We'll call them S. And so if I want to actually draw my velocity vectors, my velocities were forward up here, so I'll draw forward, and then forward in this sense is in that direction, and forward. And so what we see is that these velocities, if I kind of continue my circle around there, these velocities are tangent to the circle. Now, a tangent line is a line that comes in and touches the curve at just one point. So it's an infinite line that touches the curve at just one point. Turns out that this tangent line is always perpendicular to your radius of curvature. So no matter what kind of a curved shape, it's always perpendicular to the radius of curvature. So we don't want to call this just a linear velocity or just a velocity. We want to distinguish, because this person is running in a circle, it's not really a linear situation. So we refer to this as a tangential velocity because it is tangent to the curve. And so coming back here, we have that tangential velocity is a linear type of velocity, but projected onto a circular path. And it is a vector, meaning it has a direction. Direction is tangent to a path. And the symbol is VT. Makes sense. V for velocity, T for tangential. And the units are meters per second, because it's really just going back to our old ideas of velocity. It's really our old idea of velocity, but of something moving in a circle. The equation, we can derive this equation if we go back to our equation for arc length. And the tangential velocity was really just the distance we traveled over the time. It's distance over time. If we do this to one side, we have to do it to the other side. And we see that this here is our tangential velocity. And this here, how much angle we went through over the time it took, is our angular velocity. However, in order to derive this new equation, we had to use this one, which we had to be in radians. So therefore, our new equation, we have to be in radians as well. So that's why when we use this equation, we must always be in radians. This tangential velocity is the radius times the angular velocity. Well, the idea of tangential acceleration is really the same concept. We take our old idea of acceleration. We have somebody running track in a straight line. Now we plot out the points each second, and the distances are actually increasing. So I label these as x1, x2, x3, 3. And if I plot out my velocity vectors, my velocities are getting bigger. But what we're going to do is we're going to take this idea of a straight line and we're now going to simply curve that track. So here's my person running, and I plot out those points. Again, the points now get curved a little bit as well. And we're not going to call them x's anymore because they're arc lengths. We'll call them S1, S2, and S3. And so my velocities increase. And they get larger. Now they're again tangent to that path. And so we are accelerating. And so my acceleration, if I were to maybe use a different color, here we'll use purple. My acceleration is going to be forward for this linear track. And so my acceleration here would also be forward. So just like before, my acceleration is tangent to the path, and therefore we call it a tangential acceleration. So tangential acceleration is really just our old idea of acceleration, but now it's going to be along a circular path. It's still a vector, so the direction is tangent to that path. Symbol is a sub t, and it's a meter per second squared for a unit. The equation, we see a similarity here. We see a pattern. Again, if I take this velocity and divide by the time, we go back to our screen here, we can derive this again. If I divide this by the time, how much my velocity changed over time, my tangential velocity, that is defined as my tangential acceleration. But if we divide by time on one side, we must divide by time on the other. So this here is my angular acceleration. But remember that to use this equation, we had to be in radians. So therefore, in our new equation, we must be in radians as well. Now to just kind of recap here, the connections between the angular and the linear or tangential. Here's all of our equations that relate the two together, and we'll see that there is a pattern in that our radius is really just acting like a conversion. All of our Greek letters, we must be in radians. Radians for angular displacement, radians per second for angular velocity, and radians per second squared for angular acceleration. This will give us meters and meters per second and meters per second squared for our tangential values. So English letters are going to be meters, and Greek letters are going to be radians.